chercheurs et donc Everybody, so Tony, today you are going to present us your PhD work, and you have 45 minutes, 50 minutes to present the results, and then there will be questions, and then the deliberation. Please go ahead.
May I remove the mask while I'm speaking?
Yes,
Thanks. So thank you everybody for being here today. So I'm going to present the work I have been doing during the past 3 years under the supervision of Nabil Agadim and Aurélien Dossel here at the IAS about the cosmic web environments, from their identification, their characterization, and also the quantification of the cosmological information that they may contain. So, So astronomers are striving to map galaxies that they are observing in the sky. Here, for instance, I'm showing parts of the millions of galaxies that have been observed by the 2-micron all-sky survey. And basically, in this full sky view, each dot that you see is a galaxy, for which the distance from us, which we call the redshift, and the 2D position in the sky have been computed. But the distribution of these luminous objects that are galaxies is only the tip of the iceberg of the full matter distribution, which is dominantly made of an invisible component that we call the dark matter. And for instance, this dark matter is found in the form of the invisible dark matter halo around each galaxy that you see, and can compose up to 90% of the total mass of the system made of the galaxy and the dark matter. We can, however, even though it is not directly visible, study and evolve the dark component of the matter through numerical simulations, that is interacting through gravity based on some initial conditions that we are setting, and then evolving forward using some the law of physics. Here, for instance, in the right panel, I am showing a thin slice of the dark matter distribution from a simulation, the illustrious simulation. And what's interesting to see is that both in observation and simulation, so both the baryonic visible component of the matter and the dark component of the matter is not filling uniformly the universe, but rather stand on a pattern that we commonly call the cosmic web. And this cosmic web is made of dense nodes that are the densest regions of the universe, aggregation of matter that are shown here, for instance, in the simulation and here in the observations, that account for 11% of the total mass fraction in the universe, even though they are covering a very tiny percent of the volume. And these massive anchors are linked together by elongated bridges of matter in one direction that are called filaments, and that are containing 50% of the mass fraction in the universe. And these filaments are themselves found at the intersection between mildly dense planar-like structures that are difficult to see here in 2D, but you can think of them as the surface of a bubble, for instance, sampled with matter. And they are accounting for 24% of the mass fraction in the universe. And these walls are themselves enclosing some of the vastest regions in the universe, the most underdense in terms of dark matter, and quasi-empty in terms of galaxies, that we call voids, and that are accounting for 15% of the mass fraction, even though they are covering most of the volume of the universe. But how did we get there? And what are the mechanisms that are behind the formation, the emergence of the large-scale structures in the universe? Well, initially, the matter distribution in the universe is assumed and observed to be nearly Gaussian, with some perturbations that are evolved forward in time using through the gravity, the time, and the expansion of the universe to what is observed today. Imagine, for instance, that you have an initial spherical perturbation and that you compress it in one direction under the effect of gravity. Then you end up with a pancake-like planar structure that is a wall. If the collapse occurs in an additional direction, then you end up with a one-dimensional elongated structure that is a filament. And if the collapse occurs in the last direction, then you end up with an isotropically contracted region of the space that is a node. So to sum up a bit, the cosmic web is simply the name that we give to the late-time distribution of matter, and that is made of nodes, filaments, walls, and voids, and that is observed in both observation through the galaxy distribution or simulation through the dark matter distribution. So why are these environments so interesting for cosmology and astrophysics? Well, first we can use the environments to assess and develop some theories about the formation and evolution of galaxies, for instance, by asking questions such that does a galaxy that is living in a node environment, in a very dense environment, has the same properties, the same ability to form stars, the same mass than a galaxy that is living in a void, for instance. But we also know that the visible part of the matter made of baryons is not only composing the galaxies, but also is found in the universe in the form of gas. And we can ask similarly whether this gas has the same properties in the different environments. And finally, we also know that the late time distribution of matter in the universe can draw different types of cosmic web. For instance, can different modelization of the universe can draw different number of nodes, of voids, of shapes for this object, and of matter distribution that are inside it that we can use to improve our knowledge and our parameterization of the universe, our models and parameters. But to be able to answer all these questions that I just announced, we need to have access to the environment based on some inputs that are either the galaxy distribution, point-like distribution, sparse distribution of objects in the universe that are tracing the underlying dark matter if you are considering the simulations, for instance. So this is in this context that I have been doing my PhD thesis. And during these 3 years, I have been mainly focusing on 2 questions from a cosmological point of view that are first, how can we identify and characterize filaments from the galaxy distribution? So based on observational like inputs, a distribution of points in the space. And we will focus on one particular, the identification of one particular environment that are filaments. And the second one is, what is the theoretical cosmological information that is contained in the different environments? So a question that is more linked with the use of the environment to answer a cosmological question. And this first question is actually tightly coupled with another question that has more data science context and that can be formulated as, how can we efficiently extract meaningful representations of point cloud-like datasets, such as the galaxy distribution, for instance? And this is this first question that we are going to address in this presentation. And for that, I'm going to present you the work I have been doing on the learning of point cloud, of representations of point cloud datasets. So first, you have to know that many datasets in science and non-science fields are coming as a set of points that are living in a two-dimensional space. This is, for instance, the case of the galaxy distribution in the universe that can be 2, 3, or 4-dimensional if you consider the time evolution, or the matter properties of the cosmic web with the density, the temperature, the velocity, and all its components that can go up to 10th of dimensions if you have access to them. And this is not restricted to cosmological datasets. For instance, in the biomedical field, you can have for a single patient, so for a single data point, a set of hundreds of quantity that you can derive, a health-derived quantity that are representing it. And you can also have up to millions of dimensions for images or gene expressions in the biomedical field, in the biology field. And the common ground to most of these data sets is that they are not spanning uniformly their input space, but they stand on a lower dimensional structure, as we have seen, for instance. Most of the distribution of galaxies galaxies is standing on a pattern that is made of the filamentary structure that is connecting nodes, so a 1D structure that is embedded in a higher dimensional setting. And this is also true for higher dimensional data sets where visualization is not possible, like images, for instance. Here I'm showing the images from the Cypher-10 dataset, and we see that even though they are very highly dimensional, they are standing on a lower dimensional structure that is sketched by this yellow manifold here. And if you have a look in this high dimensional space to data points that are far away from this manifold in yellow, then you end up with images that completely lost their structural information or the features that you observe in the initial data set. So this is with this intuition and observation that point cloud-based data sets can have a lower dimensional embeddings that we will focus on 2 types of topologies of data sets. First, the cluster types 1 that are just aggregation of data points in the input space. And in second place, we are going to discuss spatially continuous data sets that makes us think, for instance, to the filament that is drawn from galaxy distribution, if you assume that the black data points here are galaxies. And we are going to try to extract this pattern. But first, let's talk about cluster type datasets. So imagine that I am giving you a set of data points, the black data points that are shown here in the left side of the picture, for instance, and I'm asking you to give some color to each of the data points that you see, and also to choose the number of overall colors that you are using to color your data set. Well, this basically defines the clustering procedure, which is how you go from the left side of the picture to the right one. Here, for instance, I'm illustrating it with a choice of k, which is the number of colors or classes, what we call them, as we call them, equals 3. But I could have as well used k equals 2, for instance. And to cluster a data set, you can use what we call the Gaussian mixture model, which is very simply assuming that the input set of data points that is shown here in the left side of the picture is drawn from a probability distribution that is a linear combination of k known probability distributions that are here Gaussian distributions with their own amplitudes, their own positions that I'm showing as crosses here, the centers of the clusters, and their own sizes to the standard deviation that are shown as gray circles around the center. And if you were about to use this kind of algorithm in your own research or in your own analysis, you would quickly end up asking yourself questions such that, how do I choose the number of classes that I input to my that I use to color my data set? How do I compare different results that I get? Because whatever the value of k that I'm inputting, I'm always getting back an answer. So I need to know what is a real cluster in my data set. So overall, during my PhD, I have been asking this question of what can we learn on the data set from the clustering procedure itself? And to answer this question, we have been using a statistical physics reformulation of the Gaussian mixture model, in which the size of the Gaussian components is actually, there is an analogy between the size of the Gaussian component in the model and the temperature of the system. And we have been putting ourselves in the context of simulated annealing, in which we are slowly reducing the temperature, so the size of the Gaussian components at different time steps. Here, for instance, I'm illustrating the procedure on a very simple two-dimensional dataset made of 5 Gaussian clusters that you see here in the top right panel. And what we see is that even though I'm using 20 Gaussian centers that are here shown as green crosses with their variance that is being reduced as the gray circles, at very high temperature, so at very high variance, they are all collapsed at the center of mass of the dataset that is chosen here to be 0. And this is what we call a paramagnetic or ordered phase. And this is true until we reach a critical temperature below which centers start to split to describe different parts of the data, as you can see here. And by going to lower and lower temperature, we are describing finer and finer details in the input data set. So we enter in what we call a condensation phase that is characterized by these successive transitions of the clusters. And the temperature, so the variance of the first transition, can be computed analytically as the maximum eigenvalue of the data covariance matrix, so the size of the data basically. And the next ones can be approximated during the annealing. And we can use these transitions to learn something on the data set by following the value that is locally governing the transitions, that is the maximum eigenvalue of a given covariance matrix of a given component in the mixture model, which is basically describing the gamma k is basically describing the size of the represented feature by a given component in the model. And here in the bottom right panel, I am showing the evolution of this quantity, so the size of the represented features, divided by the temperature, which is the sigma square, which is the value that we are enforcing, the size that we are enforcing for Gaussian clusters as a function of the temperature itself. And what we see are basically 2 regimes. The first one where we have some bounces on this unit line that are characteristics of transitions of the Gaussian centers that are describing different parts of the data. Or we have crossing of these unit lines that are described, this means that is synonymous, sorry, of the description of a Gaussian cluster that is describing now the random inner structure of a true cluster as shown here in the small arrows that are representing the movement of the clusters during the annealing. And by using this kind of two-dimensional diagram, we can have information on the data sets independently of the number of components that are using in the model such as the number of clusters at a given scale, their size as the value where you cross the line, and how they are embedded in space. So we are now able to analyze cluster type datasets by means of the statistical physics reformulation that we have been seeing just before. And we can now move on to the extraction of structure from spatially continuous types of datasets. And first, we will assume that the data points that we are provided with are standing on a one-dimensional structure that we want to extract, and that we will model as a graph structure. So what we call, we'll try to extract what we call a principal graph, which is inspired from the principal curve formalism, which is very simply as defined as the curve that is passing in the middle of the point cloud distribution. And we are proposing a model that is based on a graph whose nodes are actually Gaussian clusters, exactly as we have seen before in the mixture model. So now we can assume, for instance, that the black dots and the orange ones are a small data set made of galaxies. And we model this galaxy distribution through a linear combination of k known k Gaussian components that are here, that are paving the galaxy distributions with centers as stars and their size through the gray circles, but adding a uniform, an additional component that is the uniform background to take into account data points that are not part of the pattern that we do not want to model with the underlying one-dimensional structure that we are trying to extract. But for now, we have simply paved the galaxy distribution with a higher level representation made of Gaussian components, and we have any idea of a continuity of the underlying one-dimensional structure that we are extracting. So to do that, we are using a graph that is acting like a prior on the parameter space, that is constraining the Gaussian centers, mu, through a Gaussian distribution that is shown here, for instance, with lambda mu, that is the precision parameter. And this is the same kind of constraints that is appearing in statistics to constrain the smoothness of an estimate, except that here the L2 norm is directly put on the graph structure through this IHG matrix that is encoding the graph topology that is 1 if two nodes are connected, here for instance, and 0 otherwise. So we have built this model of Gaussian component with the background, and we have regularized it to the graph structure. And we need now to estimate all the parameters of the model. So the amplitude of the Gaussian component, of the background, the center, the position of the nodes of our graph, basically, and the spread over the one-dimensional structure, over the nodes of the graph that are encoded by the variance in the model. And to do that, we can use the expectation maximization algorithm, which basically lead us to minimize this kind of cost function with different terms. The first one here is what we call the data fidelity term, which is measuring how much your representation, so the nodes of our graph in our case, are close to the observed set of galaxies. And the second one is exactly the same, but for the background component. And these terms are weighted by some probabilistic association that are encoding the probability of a given data point in the model to be well represented by one of the components of the mixture model. And the last term is the one that we have been introducing just before, that is the graph prior, and that is measuring how much your graph is overall smooth or short. And lambda mu is acting like a trade-off between these two terms, so between how much you want your graph representation to be smooth and giving more weight to this term, for instance, or how much you want it to be close to the observed data points and giving more weight to this one. So optimizing iteratively this kind of cost function through this algorithm allows you to extract the one-dimensional structure that is made of nodes that are connected together by a graph prior, and with robustness to outliers thanks to the background component. So we have been implementing this method, and we have been calling it T-Rex for tree-based ridge extractor, because we are and will be using the minimum spanning tree as the graph prior that is very simply linking all nodes of the graph with the minimum total Euclidean distance to do so. And the algorithm is basically providing you a smooth version of the prior graph structure of the minimum spanning tree that is shown in the left picture, for instance, as the red curve that is passing in the middle of the point cloud. And it can also handle multiple scales that are appearing in the data set to the variances that are learned during the optimization. So these sigma k that we have seen before that are shown here as the gray cycles that are around the nodes of the structure that are evolving with the linearly evolving dispersion of the data around the structure. And all of this with some robustness to outliers. We do not have branches that are standing in the background nodes, for instance. And we can also, thanks to the mixture modeling, assign to each data point of the input space a probability of being associated with a given component in the mixture model. Here, for instance, in the right panel, I'm showing as red data points, those that are most likely standing in the one-dimensional structure, while the gray ones are those that are most likely standing in the background noise. So now we are equipped with some methodologies to extract patterns from point cloud datasets, and we can ask what we can learn on the filamentary structure of the cosmic web if we represent it by the principal graph algorithm, the T-Rex algorithm that we have just built together. So first, we can ask, why are filaments so interesting? So we have seen in the introduction that even though they are covering a small fraction of the overall volume of the universe, they are containing most of the mass of the universe, half of it actually. And hence, most of the story about the formation and evolution of galaxies will happen in these environments. And we can ask what is the role of filaments if we are able to identify them in these mechanisms of formation and evolution of galaxies. And we also know that the baryons in the universe are found in the form of gas that can be observed from different wavelengths, from X-rays to millimeter, but in which the signal emitted by filament is very faint. So we need to resort to an easier observable to extract the filaments, that is the galaxy distribution, to then have a look at other observables and build what we can call multi-wavelength representation of the object that is a filament. So for all these physical regions, there are a lot of methods that have been developed these past 2 decades to extract cosmic web environments, and more precisely filaments that are, for instance, based on input from simulations like the continuous density field. And in this category, I'm going to discuss 2 main algorithms that are of interest for the rest of the presentation. First, the T-Web algorithm, which is making use of what we call the gravitational potential, which can be derived from the density field to the Poisson equation, and more precisely has a look at the second derivative of this field, which we call locally the tidal tensor, and uses the eigenvalues of this tidal tensor to define the environments. So for instance, a void is a region of the space that is locally expanding, so with 3 eigenvalues that are below a given threshold. A wall is only 2, filament 1, and nodes are regions of the space that are gravitationally compressing, so with 3 eigenvalues that are above the threshold. And the Nexus Plus algorithm uses the same kind of ID based on the second derivatives of a continuous field, except it's directly looking at the density field itself, and uses in a similar way the signs and the strengths of the eigenvalues to define the environments. And what's nice with Nexus Plus is also that it has this multi-scale representation of the structures with these scale space decompositions that consist in smoothing at different scales the density field to highlight different size of structures. For instance, from very wide arteries of filaments in the cosmic web or more tenuous ones. Here, for instance, you see some application of these algorithms on the same input, and you see that they lead to different but relatively close answer on the input density field. Of course, in this category, there are other methods that have been developed, like the multi-scale match filter or the disperse algorithm. And there is this other family of methods that is based on the point-like distribution of objects, so more observationally based input, like halos in simulations that are sparsely sampling the continuous density field, or the galaxies in observations or in hydrodynamic field simulations. And in this category, we have, for instance, the BZOO model that is widely used in actual galaxy redshift survey, and that consists in stochastically sampling the galaxy distribution and with parametric cylinders, and define filaments as the set of connected and aligned cylinders that are found in the galaxy distribution. We have also in this category algorithms like the minus spanning tree itself or SCMS. Of course, we have also the T-Rex algorithm that I've just presented you before. here in the left picture, I'm showing you, for instance, the set of discrete data points, discrete galaxies that are observed from a thin slice of the illustrious TNG simulation. Each black dot that you see is basically a galaxy. And in the top right panel, I'm showing the minimum spanning tree that we use as a graph pair in the algorithm. You see that locally, the minimum spanning tree is very spiky and doesn't represent the geometry of the filament that we could expect, and has a lot of spurious branches that are connecting a few number of filaments that you want to post-process usually when you are using this kind of method. And with the algorithm T-Rex, we can use this kind of graph pair and build the smooth version of this graph that is shown in the bottom right panel as the red curve that is passing in the middle of the point-cloud distribution of galaxies with some robustness to outliers, and remove some of these spurious branches that can be seen in the minimum spanning tree, and also provides an estimate of the local width of the filaments. So through the variances that are shown as the gray areas around this one-dimensional structure in red. So I will show you how we have used this algorithm in different contexts based on numerical simulations to extract different characteristics of the filament type pattern of the cosmic web. And first, using the algorithm, we can detect the filament type structure as a whole and have an idea of the reliability of the pattern that is being extracted. And to do that, we can use multiple realizations of the algorithm. Here on the left panel, I'm showing the galaxy distribution from the illustrious simulation. And by using random subsamplings of this input, we can build and stack all the realization over a map, what we call a probability map, in a frequentist meaning that is representing the frequency at which a given region of the space has been crossed during all the realizations. So stated differently, it can be seen as the probability of a given region to reside in a filament, given the formalism that we are using. And in the right panel, I'm showing I'm over-imploding the high probability cells in practice with a probability above 0.25 over the dark matter distribution that is not used as input. We have been using the sparse sampling of galaxies that is shown here. And we see that there is a good agreement between the high density ridges of the dark matter distribution and the high probability cells that are shown in red that are favoring it. So we are able to compute the reliability of the overall pattern, and we can now address the problem of estimating, extracting from the very same input individual filaments together with their own characteristic to carry, for instance, statistical analysis. And this can be done using a single realization of the algorithm and defining, for instance, filaments as the branches of the graph structure. Here in the top right panel, I'm showing I'm illustrating this definition of a very simple toy data set. And what we see is that we can define branches of the graph as the set of nodes and edges that are connecting extremities to bifurcation or bifurcation to bifurcation that is not seen here in the graph structure. Here, for instance, we have 3 filaments. And we can derive for each of them some characteristics like their length, Euclidean or geodesic length, their curvature, their density, or their average radius. And we can also, through the probabilistic modeling of the mixture model, associate to each galaxy of the input a probability of residing in a given filament or to the background. Here, for instance, I'm showing this on the galaxies from the illustrious TNG simulation that I've already shown before. And you can see that each color is representing a group of galaxies that are most likely residing in a filament that is defined like that. That is represented as a portion of the graph of the black structure that is passing over it. And the gray data points are those that are more likely described by the background that we consider, for instance, being in walls or voids, and that we do not want to represent by the one-dimensional structure. But with this graph structure, we can also associate galaxies that are residing in nodes through bifurcations, and more precisely dense bifurcations of the graph structure. And this is, for instance, what I have been showing here, what I've been doing here, sorry, on the set of hundreds of thousands of galaxies from the Eagle simulation, in which we have been applying this very same classification scheme based on the graph structure that I've been showing you before. In the top panel, I'm showing the galaxies that are in red, the galaxies that are most likely to stand in these nodes, these dense bifurcations, while the green ones are those that are from the most likely standing in filaments. And I'm discarding the ones that are most likely standing in the background nodes. And on the other hand, we have been provided the results of the Nexus Plus algorithm based on the dark matter distribution of the Eagle simulation. And we have used the very same classification on the very same data set of galaxies with the same color code that is shown in the bottom panel. And what is interesting to see is that even though the algorithms do not have the same formalism and the same inputs with galaxies or the dark matter density field, they are agreeing on what is residing in filaments. For instance, here I'm showing that actually 70% of the galaxies that are found as being in filaments by Nexus Plus are also found as being as such by our algorithm with the sparse sampling of galaxies. And finally, we also used the T-Rex algorithm to study the interactions between nodes and filaments in the cosmic web. So we know that nodes are fed with matter by filaments in the cosmic web, as shown here in this video in the top left panel. And we can expect that the number of filament a node is connected to, which is a quantity that we call the connectivity and that is noted kappa, is linked with the dynamics and the structure of a cluster and its morphology. So to study that, we have been carrying a statistical analysis on the catalogs of clusters from the Illustris TNG simulation. So based on 2,500 clusters from the simulation on one hand, and on the other hand, we have been using the galaxy distribution, 3D galaxy distribution from the simulation to extract the principal graph with the T-Rex algorithm and compute around each of these halos the connectivity, that is the number of filaments that is crossing a given sphere around centered on the halo. Here, for instance, in orange, I'm showing a cluster with a connectivity of 3, and in blue, a cluster with a connectivity of 5. And with this analysis, we first confirmed that there is a mass connectivity relation that was exhibited also by previous work with more massive clusters that are more connected to the cosmic web. And we also report a link between the connectivity and the dynamics of the cluster. Here, for instance, I'm showing the evolution of the mean connectivity as a function of the mass of the cluster in different mass beams, as we can see, and for two populations of clusters. First, we have in blue the young dynamically perturbed clusters that are fastly accreting, that are more connected to the cosmic web at fixed mass beam, as we can see, than their old dynamically relaxed and in slow accretion phase counterpart that are shown in orange. Oh, sorry. So we have been showing just now that there is a link between filaments and the physics of some objects in the cosmic web, like clusters, for instance. And the literature is also showing that this is also the case of galaxies with filaments that are shaping some properties of galaxies. And we can ask whether filaments, and not just filaments actually, but all the environments can be used to have information about the universe itself instead of its component. So this is how we are moving to our last part of the presentation, in which I'm going to talk about the work I have been doing on the extraction of cosmological information from individual environments of the cosmic web. The question I have been asking during the PhD is, what is the theoretical cosmological information that is contained in the cosmic web environments? And let me be a bit clear about this question. When I mean theoretical, I mean I want to probe both large linear and small nonlinear scales. So we are using simulations to do that. Cosmological information means that we will have a look at a set of 6 cosmological parameters and the constraint that we can get from them compared to a more usually used statistics, more standard one. And cosmic web environments means that we need to have a definition for the environments. We have seen that there are different definitions, and we also need to have a statistical estimator in each of them. Because indeed, in cosmology, we need some compressed mathematical representations of the density field, the fields that we encounter, like the dark matter density field that is shown here in the left panel from an n-body simulation. And such centered field can be, for instance, modeled by having a look at the variance of the field, which defines the matter power, which defines, if you have a look at the distribution of matter, the matter power spectrum that is shown here in the right panel, and that is telling us how the variance of the field is distributed basically over spatial frequencies that are shown in the x-axis here. And this quantity, the matter power spectrum, is actually very sensitive to variations of the cosmological parameters. So here, for instance, I'm focusing on a set of 6 cosmological parameters in this analysis that are the matter density in the universe, omega m, the baryon density, h, the Hubble parameter at equals 0, which is the expansion rate of the universe, and s, the spectral index, the slope of the initial matter power spectrum, and mu, the sum of the neutrino mass. And sigma 8 is not shown here, but is the clustering at a scale of 8 megaparsec. And what we see is that when we are varying individually these cosmological parameters, the shape and the amplitude of the matter power spectrum is changing, and we can use this information to constrain our model and our parametrization of the universe, sorry. And this is actually what is done, for instance, by using not the matter power spectrum, the galaxy power spectrum in actual galaxy redshift survey to obtain the values of these parameters. And the question I'm asking here is, what if we are not using directly the full matter distribution, but only the one that is residing in one of the environments or their combination? So to do so, we are using a set of n-body simulations. So starting from the discrete set of dark matter particles, we are first computing the continuous over density field using a spline interpolation method. And then we are solving the Poisson equation to have access to the gravitational potential, from which we have seen that we can classify the environments based on the number of eigenvalues of the second derivative of this field that are below a given threshold. So this is what we have been implementing, and that I'm showing here on a slice, for instance, at the cell level. And we can propagate this classification at the cell level, at the particle level, and have, for instance, only particles that are residing in voids, walls, filaments, and nodes, and we can compute sub-density field based on these sub-data sets of particles that I'm showing here, for instance. And based on these different fields, we can extract our favorite summary statistics in each of the environments that is here in our case based on the power spectrum, and compare it with the overall matter distribution that is shown in the top side of the picture. So we have been applying this classification scheme on the set of simulations of the Kirote suite, which is a very large set of simulations made of more than 44,000 simulations that are spanning more than 1,000 cosmological models on a 1 gigaparsec per H box, and with 512 dark matter particles and neutrinos in case of massive neutrino simulation. And based on that, we have been here, for instance, I'm showing in the right panel the spectra that we get for the matter power spectrum, for the matter distribution, sorry, in black, and for the other environments in other colors, for the fiducial cosmology of the Kirote simulation, which is consistent with the Planck 18 cosmology. And the gray beans are those that are not used in the analysis, that are above 0.5 H per megaparsec. So the first thing we see is that filaments, for instance, are at large scale containing most of the power of the field, while it is the nodes that are contributing mostly to the power at smaller ones. And the other thing that is interesting is that they have different shapes and different amplitudes. So they may have different dependencies with cosmological parameters that we can use to improve the constraints that we will get from the matter power spectrum alone that is shown in black. So to quantify the amount of information that is carried by a given statistics, in our case, the power spectrum in the different environments, we can use the Fisher formalism, which allows us to derive the errors that we get on the parameters. And it is based on two ingredients that are the derivative, so how your statistics is varying when you are varying cosmological parameters, and the covariance that is encoding somehow the correlations between the coefficients of your representation, so of your Fourier modes in our case. And both these quantities can be derived numerically from the Kirote simulations. And this is what we have been doing on the set of 15,000 overall simulations. And here, for instance, I'm showing the results of this analysis with the first line that are the errors, the marginalized errors that we get for each cosmological parameters with the matter power spectrum alone, and the other rows are showing the improvement factor that we get for the 4 individual environments or their combination. So discarding the matter, but just using the information contained in the different environments. And the first thing we see that is interesting is that individually, the environments are constraining better the set of 6 cosmological parameters than the matter power spectrum in almost all cases except for the nodes and for the parameters that is the sigma 8. And we see also that some environments are performing particularly well in for some cosmological parameters, like for instance expected by the literature, voids are well constraining the sum neutrino mass, or filaments are well constraining the omega m. And more strikingly is that we have this combination of the 4 environment that is bringing down the constraints to up to 17.1 improvement factor for NS and 15 for the sum neutrino mass. And the Fisher formalism also allows us to have a closer look at some pairs of cosmological parameters. Here, for instance, in the top panel, I'm showing the confidence ellipses that we can derive from the Fisher formalism in the plane of sum neutrino mass omega m, and in the bottom one, I'm showing sum neutrino mass and sigma 8. And the first thing we see is that the black ellipse that is showing the matter power spectrum is strongly elongated in one direction. That is showing the degeneracy that you have in between these 2 parameters for the constraint that you can, that is limiting the constraints that you can get from the matter power spectrum alone. And this is also observed for some of the environments, but for instance, the filaments and the void power spectrum are getting almost orthogonal ellipses, which means that they are bringing a different type of information in this plane that can be used to break the degeneracy, and when combined all together, improve the constraints that we get on over the matter power spectrum alone that is shown in the blue ellipses. And this is also true for other pairs of cosmological parameters like m nu sigma 8 or other ones in the analysis. So for now, I've been mainly focusing on real space, but we know that in real life, the sources that we are observing are getting, the position of the sources are getting distorted by their peculiar velocities, which is an effect that we call the redshift space distortion. And this is an observational effect that we have been trying to take into account in our analysis to see the constraints that we will get in this space. Here I'm showing, for instance, a thin slice of the one of the simulation. You have the real space in the top and the redshift space in the bottom one. You see that some structures are elongated in the line of sight direction that we assume to be here the y-axis of the plot, and we see that clustered type regions are really elongated in this direction. And we applied the very same analysis in this space. And the first thing to note is that the matter power spectrum alone is increasing the constraints up to an order of magnitude over the real space ones. For instance, in sigma 8 and m nu, the constraints are much tighter in redshift space. And still, the combination of the environments can lead to non-negligible improvement factor over these ones that are for NS 2.3 and 2.4 for the sum neutrino mass. So in conclusion of this part, we have seen that environments can be used individually and all together to constrain better the cosmological parameters than the matter power spectrum. And this improvement is observed in both real and redshift space with up to 17.1 improvement factor in real space and 2.4 in redshift space. And even though I'm not showing it, it's observed at all considered scales in the analysis, from a large one, linear one, and non-linear ones. And there is also a low dependency of the constraints that I'm showing you with the parameter of the web finder, which is the threshold of the eigenvalues in the T-web formalism. So I hope that with this presentation, I have convinced you, at least a bit, that cosmic web environments were of crucial importance for cosmology. For instance, we have just seen before that we can use them to improve the constraints on cosmological parameters over more standard statistics that are derived from the matter only. But we have been doing that using the dark matter distribution, the dark matter particles of the simulation. So what about a bit more, a step closer to observations that are halos of simulations in the simulation, but that will need to take into account the different biases that can appear when you are using a bias tracer of the matter distribution like halos, and an update of the environment definition to, because we have been based the analysis on the dark matter density field here, which we will not have access by this sparse tracing of the matter distribution. And we also know that, for instance, bias can come with additional degeneracies with cosmological parameters. So we could use other statistics to improve the constraints that we can get from the environment. For instance, the cross spectra, what is the information that's carried by the cross spectrum between voids and nodes, etc., or higher order statistics like the bispectrum. And on the other hand, we have also used the principal graph formulation and representation of the filamentary pattern of the cosmic web to identify filaments from galaxies in simulation. And we can wonder how to apply it to actual galaxy redshift survey. We have been seeing just before that there are some redshift space distortions that are appearing that we need to take into account. And we have been studying some properties of the cosmic web filamentary structure and linking them with the properties of some clusters in the simulations. And we can ask that what are these the impact of other filament characteristics more than just the connectivity on the dynamics and properties of these clusters. And finally, overall, my thesis was done in the context of answering the question, how can we extract the maximum of information from the distribution of matter in the universe? And it inscribes itself in this upcoming and recent availability of data that are, for instance, planned by the Euclid Survey or the Vera Rubin's Observatory. And it is essential that these observational and simulation also achievements are coming along with state-of-the-art methods to analyze this huge amount of data. And for that purpose, of course, machine learning algorithms are a very strong option. But if we want to do that efficiently, we need to be able to understand them. And we have been seeing, for instance, that statistical physics can help in that. So in a very simple clustering procedure, but there are leads in the literature that are showing that statistical physics can help in the understanding of more complex algorithms like neural network and all. So in the end, I will just say that this is only with the effort of multiple communities from computer science, cosmology, statistical physicists that will be able to handle the complexity of such data sets with these types of algorithms. So I thank you all for your attention during these a bit more than 45 minutes.
So thank you very much for your talk, for the presentation. So we are going to go to the question session now, and we will start with the viewers. So first one is Oliver Han. Okay.
Kind of. So okay. So thank you very much for this very nice talk. It was a pleasure to read the thesis and to listen to the talk. I think it's very, very interesting stuff you've been doing on two diverse aspects of this beautiful applications to the cosmic web. So maybe I'll just try to pick one question for each of these. So if you mentioned here how to apply identification on actual galaxy redshift surveys, maybe you could say a few more things about the problems you foresee for your cluster detection, but then also this ridge detection or the web. How do you expect signal to noise, for example, to lower signal to noise to impact your results?
Okay. For the clustering procedure, so I need to take you think, or can we? Okay. So the clustering procedure is only at the state of very preliminary results, and indeed far from being applied on real data, because, for instance, we have been assuming this spherical shape of the clusters, which prevented from using it on actual, but on actual data. But it can be, I think, released by putting, for instance, the annealing on the. I've seen some papers on that on the annealing parameter on the eigenvalue of the ellipsoid that you are considering instead of the true size of the cluster spherically. So I think this can be one option to apply it to real kind of data. And for the ridge detector, the principal graph, I think we can somehow already be, it can already be used on actual galaxy redshift survey. But I think that it can bring more than just that if you apply it right now by handling, for instance, the blurring that is due to the photometric survey in 3D that are large errors in the estimation of the distance of the galaxy from us, which is creating these elongated shapes in the line of sight direction, also exactly as the redshift space distortions, but for all the pattern and not just the most clustered ones. And I think that this can be handled in the formalism by relaxing the constraints that I've been showing you, the spherical constraints on the variance of the nodes that can be elongated in the line of sight direction, and that can help to handle better observational data, I think. And about the signal to noise ratio, I think there is not much to improve because you can already a bit end-link it to the amplitudes of the Gaussian components that can represent different parts of the data, even though we are indeed assuming a uniform background component, but if we have a better understanding of the outliers and signal to noise in different spatial location of the survey, we can adapt it and represent the filaments, most tenuous filaments in dense environments or less dense ones. I don't know if it answers the question, but in these two aspects that I'm thinking of, and also the masking that can appear in some galaxy redshift survey, because you are not observing all the sky, but sometimes parts of the skies with holes, etc. And I think that this can be handled also through the graph pair that you are using, depending on the minimum spanning tree. I think is not much affected by these masking effects as much as if you were, not as much as at least as if you were using the DTFE to extract the density field from the galaxies.
So my understanding is also that you're not using right now. This is just a crazy idea I have. You're not using so when you do your annealing to find the clusters, you're not using the bifurcation points in the end to construct the graph, right? That information about how the point set bifurcates is that used in the graph construction, or could it be used if it's not used?
You mean the simulated annealing for the graph?
Well, yes, because I guess you have your Gaussian mixture model, and you have these bifurcations. Do you think that has a connection, or is that already providing a basis for the graph?
I see that. No, we are not using at all the statistical physics formulation of the clustering in the algorithm of the extraction of the principal curve. But indeed, now you mentioned it, it can improve the bifurcation points. For instance, here you see one of the default of the algorithm where you have this branch that is describing, I don't know what inside this Gaussian cluster that I have been simulating. And maybe I have it, but I have been applying one simpler model than the one that is learning the variances and all. So let me grab the slide. Here, where you see that on the same kind of data set is getting better in the bifurcation center because of the annealing. So indeed, it could help in these areas. But here I'm using the same fixed scale simulated in the simulated annealing, the fixed variances and spherical variances that are learned, but through the diagram that is shown here, and not learned exactly the same way as in the principal curve algorithm. But I see the point, and yes, it would be a point of improvement for the bifurcations indeed, if you consider them as Gaussianly distributed. Yeah.
Okay, thank you. Well, just one last question about the second part, then I'll be happy to. So when you do this T-web classification for the power spectrum in the end, how do you deal with the redshift space there?
Well, basically, we do nothing. We just apply the very same procedure, and we know that indeed some spurious filaments will be detected And for now, we just did nothing for them and just said, okay, what are the constraints that we get if we apply raw T-web on this kind of patterns? Indeed, there are some methods that are trying to remove the redshift phase distortions by collapsing the particles that are elongated in dense regions to make them spherical and stuff like that. We have not been using that. It could be a line of improvement in redshift space to see if we can get better constraints by doing that. But yes, indeed, there are some leakage of the power that is from nodes to filament, I think, because of these effects in redshift space.
You might be worried because some of these finger of the odds might be picked up as filament. And
yeah, I have, I think, a slide that is showing the result of the classification.
On the other hand, you might be able to do exactly that on the observatory. If it helps, it helps.
Yeah. Somewhere. But I thought I have it, but I don't. Sorry. No.
Yeah, one very last piece, really curious. So you showed that the cluster environment basically did not, singling out the cluster environment did not bring much additional information. Do you think that's because either the power spectrum is completely dominated by that, and so that's basically the same, or do you think we should take and say, well, cluster cosmology is not a promising thing?
Yeah, so indeed, one of the striking stuff in this table is that nodes are getting the lowest value of the constraints for almost all parameters, with only omega m and mu that are above 1 improvement factor with mapping power spectrum. And I think this is in part due to the correlation. So this I have them, I'm sure, of the correlation between the Fourier modes in the different environments. So here, for instance, I'm showing, let's have a look at the real space only. So the top row, you see the correlation matrices in real space. So you see that you have some strong correlations at scales above 0.3 here that are limiting the power, the constraints that you get in this with this statistic that is the matter power spectrum. And if you have a look at the individual environments, so just the individual environments are shown as the block matrices that are in the diagonal here, basically. You see that for void, the walls, filaments, you have very few correlations, while for nodes you have even more correlations at lower scales, above 0.2 h/megaparsec in practice, that have the same amount of correlation than the matter power spectrum at smaller scales, which is preventing, I think, this environment from getting nice constraints. But yeah, this is one of the reasons, and maybe it's not the only one. And the other thing is that sometimes people are using indeed clusters to improve the constraints, but they are not using, here we are using really the matter distribution inside it. They are using some halo mass function or other properties of nodes of clusters to improve the constraints, and that are working much better than just using the, I have it, but from another paper from Christina Kreisch, I think, was using the the halo mass function to improve the constraints, and where she finds that actually you improve the constraints and not lower them down compared to the matter power spectrum in real space and on the same simulations. So it's encouraging for the use of clusters for cosmology, but maybe not the matter that is resigning. Here, for instance, the halo mass function is shown in blue, the constraints that you get from this. And for instance, it's especially striking for the mu sigma 8 plane, where you have a huge breaking of the degeneracy with the matter power spectrum that is in red. Right. So I think this is one of the reasons, but yeah.
I think I asked enough.
Thank you very much. Thank you. The second reviewer is Alice Loika.
Thank you very much. Thank you very much for inviting me. Tony, congratulations for your talk and for your remark. So I took a lot of pleasure in reading it and to listen to you. And I hope I could learn a lot of things. But I think I still need your very kind help with answer maybe to some questions. So you spoke. Oh, I can read like you a little bit. So you spoke about simulated annealing. So, well, I think we have common points. I'm a mathematician, so I see everything is a point. So I was very angry with your very first slides. But I like also formula. So when you speak about simulated annealing, I couldn't understand very well what is the cooling schedule you use.
Ah, yeah, okay. Yes, indeed. We have been trying different steps of cooling so that we see the different conditions. But yeah, indeed, there's no particular.
Since, well,
Yeah.
classically speaking, simulated annealing guarantees convergence towards global optimum.
Yes.
So therefore, you use this together with expectation maximization to
Yes,
overcome the
exactly.
problem given by expectation maximization. Somehow, there is an interest here to know at least numerical performances of this cooling schedule.
Yeah.
Okay. Good. So we will meet again. So this is the plan. So we'll speak about this. So so I was very happy you citing our papers, but now I'm convinced I'm old. So I have to accept. I have to read my texts from far away. But now I remember somehow of your method was reminding me a book of Duda and Hart, where they were speaking about fuzzy k-means.
Okay. Yes. Yes.
So can you specify this kind of link with the?
Yeah, fuzzy clustering. I think fuzzy k-means was introduced in the context of to improve the k-means algorithm. Maybe you can find this slide. Basically, the k-means is just a hard clustering in which you are attributing to each. Let me have this one maybe. To each of the data points here, a hard probability that is just 0 or 1 of being in a given cluster, which are found by just splitting the data and moving the centers to have the center of mass of the representing data by a given component in the model. And I think that fuzzy clustering was introduced to incorporate the fact that you can have multiple association of a data point to multiple clusters. So it introduces this probability in the same way as what we do here with the Gaussian mixture model. I don't know much about the differences exactly in the formalisms, but the idea is to introduce this probability that a point can be in different cluster, and hence you have this probability of xi being in mu k being one of the different clusters. But I don't know how it's computed and how it's different from the probability that you get with the Gaussian mixture model.
Okay, so I remember there was a link. There is a link between fuzzy k-means and the expectation maximization. Somehow the fuzzy k-means is a kind of quickly implementation of a EM solution. And there is also, I feel like there is kind of relation, but I'm not sure with hierarchical clustering somehow. You specify something in one of your papers about it.
Yes, I mentioned hierarchical clustering because in hierarchical clustering, you do not have much this problem of choosing the number of classes. It's, I think it's building somehow some of dendrogram of the data that are linked interactively depending on the distance. And by doing that, you then have to cut at a given.
That's exactly what happens when you when you cool down your temperature.
Exactly. So this is why I mentioned it. I mentioned it because this is. I think you can build somehow the same kind of dendrogram with using this cooling schedule and all. And it doesn't assume a shape also for the clusters, which we are at a given size, of course, but we are. So yeah, this is in that sense that I was referring to that.
Okay. And I don't know if this question has any cosmological meaning, but somehow I would like to ask if it is possible to extend your approach by using also characteristics of the galaxies, like mass, type, luminosity.
Yeah, I think we could.
And,
Oh, sorry. Actually.
Can you describe this
Yeah.
in few words?
Yeah, okay. I never actually thought about that before, but this could be a good idea to give some weights to the data points depending on.
For instance,
some of the properties.
trying to find all filaments with spiral galaxies or
Yes.
something like this.
And yeah, we could include some weights. Where do they intervene? In the formalism is still obscure to me, but yeah, we could move the clusters depending on some weighted representation of the probability. So you can weight the probability themselves, the responsibility of the data points with respect to clusters, the centers of clusters, depending on some observed quantities about the data points, maybe yeah? Density, velocity, or whatever you want, properties to follow. So.
And the last one, I promised the last one. So can you specify a little bit of your details, because you average your graphs using a bootstrap procedure, and about the distribution you use for your bootstrap procedure?
Yeah. So indeed, to assess somehow the reliability of different patterns of the detected patterns, we are using this bootstrap. You are referring to that to the bootstrap subsamplings of these data points. So we are taking randomly a certain percentage of this data multiple times and running the algorithm.
Randomly, how?
Chosen uniformly randomly. So each data point has a sample to be picked. In the true parameter is the proportion of data points that you want to pick, and depending on if you are taking only 20% of the data, of course you are removing some parts of the pattern that are not detected, and hence the map would be a bit large scale coarse approximation of the pattern. But if you are keeping it at a quite high threshold, like I think we've been using 70 or 80% of the galaxies multiple times, here 100 of times, and I'm just stacking them on a grid with a given size that is shown here, and just computing the average of all the nodes and edges of the graph that are passing in one of the cells during all the realizations.
Okay. Thank you very much, Tony. So if there are a lot of questions, is that this was really very interesting, and it is really a great pleasure to read your work and to follow your answer and the presentation. Thank you very much. And I give it.
Yeah, thank you. So move now to the other committee members. So Sandrine.
First, I'm going to thank you because it was really a real pleasure to read your manuscript. And I was very impressed actually by the quality.
I don't hear Celine well.
Sorry, my voice is too loud. So I wanted to really congratulate you for the quality of this manuscript. I think it was really mature, very well documented, very well written, and I was really impressed. Also by the amount of work you've been doing in 3 years, which is really an original and interesting work. So congratulations for that. And your talk was also in the same vein today. So I have plenty of questions because I'm very enthusiastic about your work. So I probably can't ask all of them now. So I'll pick a few of them. Okay, so for instance, you've been talking about how from applying your algorithm to the galaxy distribution, you can have an estimate of the width of the filament. Do you have an idea of how it would compare to, say, the width of gas filaments you'd found in your hydro simulation? Is there a connection between this filament width you have from the galaxy distribution and the one from the gas?
So I don't
Do you have an idea?
I don't know the one from the gas. I have been applying it indeed in 3 different hydrodynamical simulations that are Magnetica, Eagle, and Illustris on only the galaxy distribution, and derive some width property of filaments, some radius that are that I sum up as radius of individual filament through the average, basically, of the local width of the branch. And I have not been comparing this with the. I'm not aware of the radii that we get with gas, so I'm afraid I can't answer. But I think the gas is more extending than the galaxy distribution, but I have no order of magnitude to give. I think it's more spread, but in my opinion, but how much I don't really know.
So now I have a question about the use of this cosmic web decomposition for cosmology. So you've been saying a bit that applying these to a real galaxy distribution is going to be difficult because of redshift distortion, galaxy bias, and all this kind of effects. Have you considered applying this technique to weak lensing maps? And in your opinion, what would be the limitation or the difficulties in this respect?
Weak lensing map for the detection of filaments too?
Yes, sure, why not?
Okay.
You have 2D density maps, so you could apply, I guess, a 2D version of your algorithm on a grid, for instance. Or
So for now, we have mostly been focusing on the application on discrete inputs like galaxies here. So you are more referring to continuous types of inputs. Like
or it could be a grid, and you reduce the information of a grid on points. And
this could be done. I've tried that using not the weak lensing maps, but the dark matter distribution, where I've cut some thresholds in the density field and just get the information on the cells, so the cells that are above a given threshold, and using them as data points. But this is a bit of a dirty proxy to get a discrete representation to input to the data. So I don't know if there are not better suited methods that directly handle continuous fields like disperse, for instance, to be used on this kind of data. But I think it can be done if there are some features that are in this algorithm that are needed for these applications.
And about applying the T-web decomposition and power spectra of cosmic web components, but for weak lensing maps?
Yes, that could be done. Because, yeah. But T-web is based on the gravitational potential, but Nexus Plus, for instance, in any ways, you could always look at the curvature of your field, whatever it is, locally, and define some structures inside it indeed. So even if these are weak lensing, I don't know, you could still, yes, use the curvature information of the Asian, of the eigenvalue of the Asian, whatever the continuous field you have. So I think yes, it can be done. But, what it would be.
Can I ask another one?
Sure.
So I was wondering, so you talked about power spectra, these cosmic web components. Have you looked at the effect specifically on the BAO?
Not specifically. I think we can somehow guess them sometimes through the wiggles that we see in the derivatives of the power spectra alone, but I have not been focusing specifically on them. We are including some I was wondering if I don't think we have been doing specifically that, but we are using the scales that are around these scales of VAO, but I'm not sure about the impact of that only. That's a good question.
The reason I am asking this question is because, as you know, BAO reconstruction is difficult, in particular because of nonlinear effect. But if you were to select cosmic web components that are less prone to these nonlinearities, like nodes, you don't know, say in your filament power spectra or void, or so maybe the BAO reconstruction in that case could be easier, or maybe there is something easier to be done.
Okay, so that's a good point.
And maybe a very last one, very practical one. But if we wanted to use this, so maybe my question would be, so when you apply your T-Rex algorithm, how involved is it in terms of computing cost, and how feasible it is to apply it to for instance, the Euclid photometric survey, or with hundreds of millions, maybe billions of objects. Like, is it possible?
Billions is not. So for now, I have been mostly working with Python, so the code is still quite optimized for Python code. So for instance, just to give another magnitude, I think that hundreds of galaxies, hundreds of thousands of galaxies from the Eagle simulation takes just a few minutes or the illustrious simulation for the connectivity that we have been using takes just a few minutes, 5 minutes or so to run on a few hundreds, but it's scaling with k cube. So k being the number of nodes of your graph, basically. So of course, this k is proportional somehow, not proportional, but to the number of points that you are using. So the more the points, more the nodes of your graph if you want to behave it correctly. So it goes quickly. Difficult to run it on more than a million, but I've been using that on millions or so of galaxies on the SDSS catalog, 600,000, and it takes still tens of minutes. But I think that billions is not one aim with the actual code that I've been using. But maybe in photometry we can use some slice bins, 2D bins.
Something.
Yeah, or some parts of the chip distribution and not the entire the coverage of the Euclid.
Okay. May I have a very last question? I forgot one. It's very specific, so it should be short. I was wondering because in your manuscript you mentioned so this well, and also in the presentation, when you use the T-word, the threshold you use for the eigenvalue, and we see that so you fix it to a given value. And I was wondering how much of the information in this observable is actually in the fact that you fix the threshold lambda th and not lambda th over sigma. So how much of the information is actually on the fact that there is an information of the variance, the amplitude of fluctuation of the field at the resolution scale?
You mean the lambda th for the T-word formalism?
Yes, exactly, because when you change cosmology,
yes,
the variance of your field changes at the resolution scale.
Oh, okay.
And if you fix lambda th over sigma, so you have a threshold in terms of number of sigma instead of dimensional value.
Okay. Okay.
There is a variation of cosmology variation here, and I was wondering how much of the overall cosmological information is actually in this term. I don't know if you have any idea.
Yeah, not at all. What we've been doing, however, is to use different values of lambda threshold, but indeed the same for all cosmologies, and have a look if it has an impact on the classification, and even including as the Mison's parameter that I'm not showing in the presentation, but in the manuscript.
So maybe something you could do, for instance, would be to so you have a plot at some point in your manuscript where you change the cosmology and you see the impact on the abundance of each object of the cosmic plot. So what you could do is do the same, but now fixing lambda th over sigma instead of lambda th, and you would see whether the difference is getting much smaller or not.
Okay. It's not something I've been doing, so but if this is the case, then it would be a good idea to have a look at how much this information is corrupted, if I can say that, by this. So indeed, you are referring to this, I think, the different mass fraction that we have in the different environments with the different values of lambda.
Oh yes, it could be this one. This is not the one I had in mind, but I was thinking of about 6.3. Yes.
Ah, yes, this one. Okay. Yeah. So indeed, we have here the mass fraction, average mass fraction for all the realizations over the mass fraction of the fiducial cosmology, and by varying the threshold, we can have different dependencies.
Yeah. So instead of fixing lambda th fiducial, yes, you fix lambda th over sigma.
Okay.
And just to see if now the cosmology dependence is smaller or not.
Okay.
And thank you very much.
Thank you. So we have also two committee members online. So the first one is Simon White.
Okay, do you hear me?
Yes, very well.
Okay, well, I'd like to start by saying that I really enjoyed reading the thesis. I found it very clear and also very interesting. And I liked the way that you set out and motivated your algorithms. And I appreciated the technical level at which you explained what you had done, as well as the illustrations showing how it works on simple cases. And I thought also your talk was very clear in simplifying what in some places is technically very, very detailed in a way which was easily comprehensible to a less specialized audience. So congratulations. I thought both the thesis and the talk were excellent pieces of work, and I enjoyed it very much. So I'd like to start with a very general question and then move on to a couple of more specific aspects of it. So the dark matter distribution, not only the dark matter distribution, all the models you've been considering, is obviously a deterministic consequence of the initial conditions. And in fact, it's a kind of Hamiltonian map. There's a Hamiltonian process which directly maps the initial distribution to the final distribution in some kind of continuous way. And this mapping preserves the topology, at least on large scales. So the question I find interesting is to what extent the patterns that we see in the network that you're finding are a consequence of the Gaussian nature of the initial conditions, and to what extent is it influenced by other factors, and is there perhaps a possibility to detect non-Gaussianity of the initial conditions through the patterns that you've been looking for?
Okay, that's a tough one.
Sure, no, I don't expect you to have a definite answer. I'm just interested in your thoughts on it.
So indeed, as you said, the results that we have, the pattern that we observed, as I've been mentioning, for instance, in the introduction, is the result of some initial conditions, initial fluctuations of densities that we assume and somehow observe to be Gaussian, but there might be some Gaussianities. And I think that the question is how much the pattern that we observe today can be used to constrain these non-Gaussianities in the initial distribution. So the first answer is I don't know. And the other one is we could, however, study it through simulations like the Quixote ones, for instance, in which we have access to the initial conditions that we have been inputting and the final ones, and see how much, yeah.
Well, they are all Gaussian, of course.
Yes.
But I think what you could do is you could see, I mean, if you could define the pattern at early times and see how it evolves and how nodes, well, links shrink and cycles amalgamate into nodes and so on, the dynamical evolution of the pattern might give clues to such things. For example, my impression is that massive clusters today are linked to many more filaments than a typical high peak in a Gaussian random field. And that's because they've collapsed a number of cells into one thing, but maintained the links to the surrounding objects. But yeah, I only have a qualitative feeling about this. So I wondered if you thought about it.
Yeah, I think that this is one of the study that one of the members of the jury have been doing, in which they are studying the indeed the connectivity, as you mentioned, of density peaks in Gaussian random fields, showing that it can be computed analytically. And I think that in simulations, what we see through the nonlinear evolution of this Gaussian field is that there is a decrease with time of the overall connectivity in simulations.
A decrease of connectivity of an individual object, or
average connectivity.
The average connectivity, I see.
Yeah, something like that to show you. But this is only one topological aspect of the cosmic code.
Well, that's interesting. What's the reference? Then I can look at it afterwards.
I think this is Codice et al. 2018.
Oh, okay, so all right.
I applied if you want.
All right, that's fine. I can find it. Thank you.
Yeah.
Okay.
in which we have the value of the connectivity depending on the height of the density peaks in the initial Gaussian random field in the left panel in 3D, for instance. And in the left one, you have so if you look at the lambda CDM curve, for instance, you have the evolution of the connectivity from high redshift to lower ones that is decreasing with time. But this is only indeed one aspect of the field.
Well, that's interesting because that's already the opposite of my intuition. So enjoy looking at that. Let's move on to something more specific. I mean, you mentioned a couple of times that with your particular analysis scheme and also with other similar ones, about 50% of the mass is in filaments and about 15% or 20% in nodes. Now, sort of straightforward analyses of high resolution simulations of dark matter find at least 60% up to 90% of the mass associated with halos, which are disjoint. And typically, if you take the unsmoothed density contours and identify when they percolate and when they link halos together in filaments, you find only about 10% of the mass in the regions of the bridges. So clearly this difference is somehow related to a difference in the smoothing that's associated with the algorithm or with the sparseness in the case of galaxies. So the difference is quite large, the way I phrased it. How big are the differences between the different filament finders that you're familiar with? And how does this link to the physical meaning of the filaments?
Yeah, okay. So indeed, in what I've been showing in the introduction, if that's what you are referring, I'm showing the mass fraction with 50% of the mass in filaments. And this was obtained with one particular algorithm in one simulation analysis that was made by Cotun et al. 2014. But indeed, these fractions I'm showing here, a slide, for instance, are sensitive to the web finder that you are using. Here they have all the algorithm have been used on the same observed distribution of matter, may it be the dark continuous density field or the halos in the simulation. So this is a paper from Libeskind et al. 2017. And you see that indeed there are some differences if you have a look at the mass fractions in terms of cells of the dark matter distribution or halos in the right side of the table. You see that in film, if we have a look at filaments, it goes from 20 to well, even 10% of the mass fraction to 62 even with this first algorithm. So there are some strong differences with the finder that you use that are mostly based on the different formalism. We do not have, they do not have the same definition for filaments. There are no unique definition, actually. Some are using the information coming from the velocities, the density field itself, the curvature of the density field, or the gravitational potential, as I've been talking about with the T-Web, for instance. So I think that the differences are mostly coming from that, these different formalisms that we have, more than smoothing or anything like that.
I think that's correct, but they are quite large. I mean, people like me who've focused on the dense regions would argue that if you were not limited by resolution, you would find more than 90% of the mass of the universe is actually in collapsed objects, which we call halos. Yes. A lot of it in very small ones. But the filaments that you're finding clearly have some reality. And so it's interesting to ask, what is the relationship between viewing things on the kind of large scale structure scale and seeing on the small scale? But perhaps in your last chapter where you looked at the cosmological variables, you used T-Web rather than T-Rex. Yeah. And so I assume this was mainly for some historical reason, that you didn't have T-Rex ready at the right time or something. But do you have any idea of whether using T-Rex would change any of the conclusions, or whether there would be quantitative shifts in things with the different filament finder?
So yeah, it's not really historical. It's more than we had T-Rex ready for this use, but we wanted to have a look at the distribution of dark matter and so the particles and not halos to avoid dealing with because T-Rex is working with halos basically on dark matter. It would be, as I mentioned before, it would be difficult to run it on the very large number of particles and for the number of simulations that we use for this analysis. So it would have taken much more time. So we focused on the dark matter distribution of the particles in the simulation and use the T-Web algorithm. And about the dependency of
well you could run it on the halos, I think that's right, the number of halos.
Yeah, but this would come with additional bias systems and all, no, in the different environments.
Sure,
we
of course.
would have some theoretical comparison with the matter without assuming something for the bias and all.
It's true, but it would be close to the galaxy case because
exactly. This is one of the perspectives of this work that I would like to carry on with is the use of halos, but also the halos in the Chirote simulations are quite of high mass, so the mass resolution of the simulations are not quite good.
I see.
That's a bit rough. I think they are above 10 to the 13, and if we have a look at the distribution of halo mass in the different environments, we will be only probing the end tail of filaments and the nodes and not the other environments. So we wanted to, as a first analysis, have a look at all of them and using without bias the matter distribution only.
Okay. Yeah. So at the moment, you don't have an indication of how method dependent the conclusions are.
Not directly, but by having a look at the different values that we can use for the T-Web finder, we are somehow incorporating this uncertainty that we have on the identification of the environments, because the changing these values, for instance, from 0.2 to 0.4 is showing different kinds of volume and mass fraction in the universe and different matter distribution inside them. And we have been using different values of these parameters. So even though this is the same formalism, this takes already into account somehow differences that you can have between different formalisms in the analysis without doing it explicitly, but still, I think. So the dependency is not expected to be large, except with algorithms that are, of course, finding not at all the same environments, if there are some.
Okay, thank you very much. That's probably enough for me now. And congratulations again. I think it's a very nice piece of work.
Thank you.
Okay, thank you. So the next member of the committee is Gilles Biroli.
All right, thank you. Do you hear me?
Could you speak louder?
Do you hear me? No.
Yes, I do.
Do you hear me? All right. Okay. So, well, let me first start congratulating you for the work that you did during your PhD. I mean, it's very nice to see that it went to from theoretical aspect coming from statistical physics to a cosmological application. I have to say that I'm really, let's say, I'm not at all in the field of cosmology and come from statistical physics, so I can really appreciate, for example, how much you were pedagogical during your presentation. So it was really very, very good for me. I mean, I could follow from the beginning to the very end, and it was just perfect. So congratulations. So I would like just to ask you, well, two questions. So the first one is about the method that you use. So clearly you have motivated the method using statistical physics. You show in the first part of the presentation how it works well, how it's related to phase transition. At the same time, you also said at the very beginning in your presentation that there are many problems in data science today in which data actually have a high dimension, well, they are in certain space, but actually they live in a submanifold which has a lower dimension. And one very interesting question is characterize this manifold. So maybe, I mean, the question that I would like to ask you, which is more general, so is, or maybe two questions. One is, you show that your method works well, but can you say something about the limitations? In which cases you think it would fail or we have to be generalized? So if you take other kinds of data, and then again, so in this slide, indeed, you have, I mean, the cosmology on the left, and then you go on the right in one very high dimensional problem. Do you think that you can generalize somehow your method to address some of these problems, or no, it's just too far?
Okay. So the first part of the question is, if I understood correctly, the use of the method to identify somehow the manifolds and the limitations of it, of the statistical physics formulation of clustering, you mean? That's it?
Yeah, I mean, it's the limitation, meaning the when it's not going to work. So I mean, you show with doing this, you show that it's able to identify clusters, but I mean, you could think that there are cases in which it wouldn't be. So,
Yes.
So what are these cases? When do you think what are the main limitations that you can think of?
Yeah. So the main limitation, I think, of the work about the statistical physics clustering is first that indeed you need to have some cluster type datasets as input, because the formulation and the cooling scheme and the diagram that I'm showing here in the bottom left right panel, for instance, are only assuming a given type of topology of dataset. I am looking here, for instance, at the maximum eigenvalue of the covariance matrix, while if you, in the case of the principal graph learning, for instance, I have been using the minimum eigenvalue locally to describe the width of the structure. So first, if you do not have a cluster type dataset, but a spatially continuous representation of something, I don't think it will work like that, and you won't see some interesting transition to use. And the other one is the fact that we are assuming the clusters to be, of course, Gaussian and spherical in this analysis that could be relaxed by putting the annealing temperature on another parameter than the size, the spherical size of the clusters, but still. And the other one is that we have been mainly focusing on same amplitude, the same value of pi k amplitudes for the Gaussian components in this analysis to handle the analytical part of to ease the analytical part of the formalism. So we assume somehow that the clusters have about the same number of points inside them, which also could be relaxed by taking them into account during the annealing instead of fixing the value at 1/k, basically, n/k. So this was the first part of the question, and I think that the last one was referring to the application to some of these problems. So we have been thinking, for instance, to use it for the second problem here that is shown, the matter properties of the cosmic web, in which there are some, in cosmology, there are some phases of the gas that are defined through some cuts in density and temperature planes, I think, for which we can, for instance, extend to more dimensions, more properties of the field, and have a look at if the cells in simulations, for instance, if the cells are describing some clusters in space, higher dimensional space than just these 2D features that are the temperature and the density of the gas. But I haven't been doing that, but this is one of the perspective of that work on the application of the work on statistical physics for cosmological applications. I don't know if it's clear, the application, but
yeah, okay, thank you. So my second question is jumping to the very end, actually, of your presentation. So it's about the constraint that you can put on cosmological constants. So if I understood correctly, so I mean, your work showed that, okay, people use the power spectrum to put constraint, and you show that actually it's very important. I mean, you gain if you consider the structure that is, I mean, consider the structure that come from nodes, filaments, etc. Those additional constraints that are important, and if you can consider them, if you use them, one use them to constrain, then one can get a better precision. So my question, I mean, again, I have two questions, let's say the same question, two facets of the same questions. The first one is, so you cited work that use the power spectra, but what I mean is, what is the best of the best actually? I mean, the methods to constrain the cosmological constant are the one based on power spectra, or there are others? And then the second, let's say, part of the question is that I know, again, I'm not an expert at all, but I know that people have used convolutional neural networks, and also I think things related to the scattering transform, to have generative model, and then use generative model to, again, to put constraints on the cosmological constant. And my impression is that somehow convolutional network or the scattering transform, they do, maybe in a black box way, maybe more for convolutional network than from the scattering transform, they do something that you suggest. I mean, they go beyond the power spectrum, and they try to include the fact that in the structure there are things which are non-trivial, like nodes and filaments. So is this correct? And also how the result of the constraints which come from convolutional neural network and scattering transform compared to the improvement that you found? Yeah. And again, if I say something wrong, because I'm not an expert at all, don't worry, just say you're wrong.
Okay. No, that's okay. So I'm going to rephrase the question because we can't hear you well, but the first part of the question is, how do we constrain cosmological parameters basically usually? So we are using somehow what I presented in this slide, the matter power spectrum based on some observables. So of course we do not have access to these distribution of dark matter in real life. And to obtain the constraint from large scale structures, we use proxy of that, the galaxy power spectrum, for instance, that can be observed through computed from redshift galaxy surveys that is done actually through EBOS galaxies, or I don't know what redshift survey, and you can derive the very same summary statistics based on that and link it with some additional complexity with the one of the matter, with handling some, for instance, the bias that I have been calling, that I have mentioned in the answer previously, the bias that can appear by using a tracer of the matter distribution instead of the matter distribution to get your constraints. So this is one of the ways, but galaxies, of course, are not the only observable that you can use. You can obtain the constraints, and these are using the other observables like the cosmic microwave background or other distribution of objects in the universe to get your constraints. And the second one was mostly about the use of convolutional neural networks and other derived algorithm like the scattering transform that you mentioned for the cosmological constraints. So indeed, I've seen some papers about the use of CNN for that, and read a bit more about the scattering transform, which is basically the same structures than a convolutional neural network, except the filters are not to be learned, so it's easier to handle for real data sets. And indeed, in the paper from Mala et al. 2018, I think they are showing that this goes beyond the order 2 statistics of the data by correlating somehow information up to order 3 or 4 if you are considering different layers of the network. And these have been applied and are applied on the very same set of simulations of the Chirote simulations. I think a few weeks ago, there has been a paper that is using the a change in the scattering transform to apply it in the 3D distribution that of the Chirote simulations, dark matter simulations, and they are getting comparing it to the usually used more standard statistics of the matter power spectrum alone, exactly what as I've done here, and they are showing that it can improve a lot also the constraints that you get, and I think this is linked with the fact that you get information from higher order statistics than just the second one that is shown in particular in this paper really nicely, because you break some degeneracies by just having your few scattering coefficients as a summary statistics instead of the power spectrum. So yes, if the answer is yes, it can be used, and it's actually used by some people from the Flatiron Institute and Harvard University also.
And I mean, if you can you say how it compares to what you did? I mean, I understand that it's different, but maybe philosophically, in a sense, at least, if you hear did Stefanola, is philosophically similar. So if you want to get things which are not just in the power spectrum and which are related to the fact that the texture contains wall filaments and nodes. So is I don't know if it's exactly on the same set of data, but is the kind of improvement that you get better or worse or similar to what they get?
I have I don't have the numbers in mind, but they are using the same simulation, so I could check quickly to see, and the same set of parameters, so we could check quickly. They have the absolute values of constraints are better or not, and in what cases, and it would be interesting to see if indeed the split in Cosmic Web is also somehow has the same information than some higher order statistics. But quantitatively, I don't have the numbers.
Okay. All right. Okay. Thank you for the answers, and thank you again for the presentation. So I'm done with the questions. Thank you.
Thank you.
Thank you. So now we have the next committee member, who is the supervisors. Aurélien.
So, thanks for this beautiful presentation. Very great. Well, it's always I find it always a bit weird as the supervisor questions, but since we spend many times answering questions. So I still have one just to
Closer to the mic, please.
So I was wondering, in T-Rex, basically, the thing that we're hardly grasping is the detection of the wall. So do you think do I have any idea how it could be incorporated in any way in the formalisms or using a different formalisms?
So I've been giving some thought about this and how to identify walls with the same kind of formalisms, in which I am trying to add to these K-Gaussian components here that are spherical components paving the galaxy distribution to identify the one-dimensional structure in the same way using K-prime distribution of Gaussian components, but that are elongated in two directions and collapsed in a third one to locally describe a planar structure and move them exactly in the same way and using another graph prior, for instance, not the minimum spanning tree, but I don't know the K nearest neighbor, but it's very actually on toy dataset Voronoi model, for instance, it's very sensitive to initialization of the algorithm. And but look, if it works locally, you could have access, for instance, to the width of the wall or stuff like that. But I don't know if it's something that can work from a computational point of view and convergence of the algorithm, because it's very sensitive in very simple case already. So yeah, for now I've been thinking mostly about filaments, and the extension to walls is not trivial, I think, and needs to come with some updates of the formalism.
Okay, thank you.
Yeah. That's it. Yes. Okay, Daniela.
Do you allow me to speak in French?
Yeah.
Yeah, okay. Alors, je voudrais aussi te féliciter énormément pour le travail que tu as fait, féliciter pour ta thèse. Te féliciter surtout pour le grand saut que tu as fait, parce que tu étais en poste dans un des fleurons de l'industrie française, comme les gens le disent, et tu as décidé finalement de commencer une thèse en astrophysique, en cosmologie, très très loin des aspects applicatifs. Et c'est un grand saut dans l'inconnu que tu as fait de manière parfaite. Ça a été un très très grand plaisir et finalement une très grande chance pour moi de travailler avec toi. Voilà, je te remercie pour ce privilège. J'ai quand même une question à te poser. Je ne te demanderai pas d'y répondre, mais je te pose la question quand même. Je me demande comment tu as fait pour travailler avec deux superviseurs, avec Aurélien et moi. Donc, tu répondras à ça plus tard, ou pas du tout. C'était effectivement une gageure, parce que c'était un saut dans l'inconnu avec deux aspects, deux pactes assez différentes. Je te remercie aussi du coup de m'avoir permis de travailler avec Aurélien. avec quelqu'un qui est plutôt vraiment physique. Et tout ça en jonglant avec ton background, ta formation qui en fait ne te préparait pas complètement à l'astrophysique. Tu as réussi à prendre en main ton sujet. Je pense que tu as peut-être été surpris arrivant du monde de l'entreprise de te voir proposer un sujet mal défini, pas forcément complètement abouti. Le premier sujet qu'on t'avait initialement proposé pour ta thèse, c'était de travailler sur la reconstruction du Cosmic Web. Et au bout de quelques temps, tu t'es rapidement rendu compte que finalement, il y avait énormément de choses qui étaient faites et tu as pris en main toi-même l'organisation, le contenu de ta thèse et tu l'as fait avec vraiment énormément de brio. Donc, je te remercie beaucoup pour tout ça. Je te remercie de m'avoir appris plein de choses. C'est assez bizarre quand on est superviseur de thèse de se sentir perdu. En général, on l'est au bout d'un certain temps, mais très rapidement, ça a été le cas. Et donc, ça a été super pour moi d'apprendre tout ce que tu m'as appris d'un point de vue des maths appliquées et de la physique statistique. Alors, bien entendu, après tout ça, vous direz Tony est quelqu'un de parfait. Mais il y a des aspects sombres à la personnalité de Tony. Alors, non seulement il a travaillé sur des traceurs biaisés de la matière sombre et de la matière noire, mais je me suis toujours demandé pourquoi quand j'arrivais le matin ou quand il arrivait le matin, il se trouvait dans des bureaux noirs, pourquoi toute la journée il était dans des bureaux noirs, non éclairés. Au départ, je me suis dit que c'était pour faire des économies à la recherche publique, mais en fait non, hein, parce qu'il a quand même lancé pas mal de simulations, pas mal de calculs sur des grands calculateurs qui du coup ont utilisé de l'électricité, donc c'était pas ça. Et à un moment, j'ai eu la réponse, et la réponse était que Tony fait partie de la maison Serpentard. Et donc, ça explique un certain nombre de traits de caractère, de sa simplicité, mais de sa sombre personnalité, que je n'ai pas encore fini de découvrir. Et 3 ans n'ont pas été suffisants. Ça s'est passé et ça a duré finalement très peu de temps. Donc, je te remercie pour ces 3 années de travail avec toi, pour tout ce que tu as fait, pour avoir fait avancer finalement des questions sur lesquelles on n'était absolument pas prêt à travailler. Tu as pris tout en main depuis le début et j'espère que ta carrière scientifique sera superbe et qu'on aura l'occasion de continuer de travailler ensemble si tu le souhaites.
Okay, thank you. So I am the next and the last. So I really enjoy also reading your manuscript and listening your talk. I think it was a very nice presentation of your work. And it was very interesting to see this kind of new results and how it impacts cosmology. I still have a few questions, and which somewhere are related to a previous question, especially from Simon White. So you propose a new tool and extracting filament from the web. And the way that you try to evaluate it is to compare to other results, right? And then you found that you had 70% agreement with the other method. And my question would be, what about the 30 other %? Is your method more accurate, less accurate?
So you are going to this slide, I think, where I show that indeed, when comparing the classification of the galaxies that we get with the T-Rex algorithm in filaments and from Nexus Plus, I said, and we find that we have 70% of the galaxies that are found by Nexus Plus as being in filaments in our classification scheme. So indeed, in that sense, it means that we are missing 30% of the galaxies in filaments if we consider Nexus Plus as the truth. And so first of all, there are 13% of these 30% that are missing that are actually residing in the nodes here, that I'm classifying in nodes which Nexus Plus is not. So it brings the full thing as at 83% of agreement for the overall filamentary pattern. And the others indeed are missing in the sense that we are not we are identifying them in the background component of the model. So these misclassifications could be, I haven't checked the data quantitatively, but could be in the fact that we are using the galaxy distribution, the dark matter distribution as an input. So maybe these are tenuous filaments that are traced and identified by Nexus Plus in the dark matter distribution, but that we do not sample correctly with the galaxies, the sample of galaxies that I'm using, that we are not identifying, at least with the algorithm. So in that sense, yes.
Yeah, so here we don't know if you miss some filament that the other method found,
yes,
or the contrary, right? We have not the same, right? And the second question by Sandrine, what is the width of the filaments? And then here, from what I understand, you are not able to give an accuracy of the width of the filament you are measuring. And also this is kind of important information. So my next question is that isn't there a way to have a much robust evaluation of what you are extracting from the data?
Yeah. So I've been showing you previously this bootstrap thing to get the probability of the pattern of the reliability of the overall pattern, but I have been also during my PhD and not showing there using the same kind of idea to identify uncertainties. So at the nodes level directly of the graph structure, so using multiple runs, but directly associating a spatial uncertainty to the nodes of the graph instead of plotting them on a map. And by doing that, you have some uncertainty band around the one-dimensional structure. And I think that this can be used to, for instance, have an estimate of the robustness, the uncertainty on the width. For instance, if you have all the realizations, you compute for a given part of the graph or a given filament, the width over the multiple realizations, and you can have bootstrap averages of the width end of its uncertainty.
But isn't it more convenient to have a kind of toy model or kind of realistic toy model, semi-realistic toy model, where you know exactly where are the filaments, what the size of the filament, what the width of the filaments, and then to have a robust evaluation on the method and then a comparison with the other method as well?
Okay, I see the point. You are referring to using something that we know is true to assess the different methods, and in particular the one I've been developing. And to do that, indeed, we can use I've been implementing this Voronoi model, which is a very simplistic representation of the cosmic web with lines and nodes and planes, real planes that are intersecting at the lines level that are making filaments. I have maybe a small visualization in 2D here and in 3D that I'm using sometimes in the manuscript. And indeed, in this case, we can know we can input the size of the filaments of walls and all and have a quantitative comparison. For now, I've been only doing that for qualitative pictures and say that, okay, we are passing in the middle, but I have not been carrying any quantitative analysis. I think this could be done with these simplistic models, Voronoi models, yeah. For instance, indeed.
Okay, that would be one way to go. There is also some statistical process like the Cox process, where you know how many filaments, what the size and the width of the filaments. Then you can see if you recover properly this kind of information. That would be another way, at least to have a partial information on what you extract and accuracy of what you extract. Yeah. Okay. So the first part where extracting a descriptor from the data, and the second part was connecting to the cosmology and deriving parameters. So here also you have the Voronoi here, which have been used in cosmology, but also bispectrum, Minkowski function. Also, there are many methods, and somewhere here we can wonder if this new approach will bring anything new compared to I don't know, bispectrum or Minkowski functional. And any idea and any reason why you believe that, for instance, these techniques would be better than Minkowski functional, which also is a kind of geometrical statistical information.
Are you referring to the classification
to the deriving of cosmological parameters
yeah.
from what you derive from the data?
Okay.
Yeah.
So indeed, there are a lot of descriptors for the matter density field. I've been citing only the power spectrum because this is what I'm using here. But as you mentioned, there are a lot of topological tools. Julia also mentioned the use of the scattering transform or translational network that can be used for that purpose. What about the use of that over bispectrum, for instance? I think that bispectrum are quite difficult to compute, even though recently there are some literature that is being made to improve the computational complexity of these higher.
Bispectrum is used for years and years on real data. And, so it's something which is very common in cosmology. Yeah,
okay.
And there are fast algorithms as well.
Okay. Yeah. We have less coefficients also. Maybe I don't know if it can come into play than the bispectrum description, for instance. I think the length of the data vector of the statistics are smaller than in the bispectrum case.
So okay, so you have no real physical intuition why this should work better.
Why this should work better? No, and I don't even know if it actually works better or not. There is this paper from Shanghun et al. Who are using the bispectrum of the Kyoto simulations, but on the halo distribution, so it's not directly something we can compare. So I don't know how it compares with higher order statistics, but that could be interesting to see if there are more or less information that the bispectrum that is contained in the combination of environments, but I don't have considered.
Okay, so then you show that when you go to real to redshift space, then the improvement decreased significantly, right? So you had a more than order of magnitude improvement with shift to around 2 improvement, right? So this is certainly due to this finger of God effect, right? But there are some way to correct, right, the distribution of galaxies from finger of God. Isn't it something you could have tried to go from somewhere in redshift space to transform to real space and then apply your technique? Is it something that could be possible?
So indeed, with the distribution of matter here, there are some methods that are trying to reconstruct to collapse the elongation in the line of suggestion to spherical things to get back to real space. But the effect of redshift space is quite random and induced by the velocity. So in reality, it's hard to handle them. You mentioned the galaxy distribution. I think there are some Bayesian forward modeling that are trying to go from the distribution of galaxies like Bohr, for instance, or Markov algorithms that are going from the galaxy distribution, trying to infer the initial conditions and then make it evolve forward in time, which allows you to have the distribution of the matter in real space. So this would be a way to go from unobservable that is the galaxy distribution and go back in real space with the full matter distribution and applying this kind of method. And about the improvement themselves that we see here, that they are compared with the matter alone, which is getting much better in redshift space than real space. I think that this is mostly due to the fact that monopole and quadrupoles are getting different kinds of information that break over some degeneracies. But it will be interesting to see if this is also the case in at least as much in using halos in the simulation, for instance, instead of more absorption-like distribution closer to galaxies. If the matter power spectrum, halo power spectrum, is getting a much tighter constraint or not, and if the environments are getting better improvement factor in redshift space due to that. So yeah.
Okay. I was wondering also, you came to the cosmology, and at some point when you're not interested in applying your technique on real data, you are using only simulation here. Oh, that's the fault of Nabila. Okay.
No, that's my fault. I prefer simulations. Everything is more simulation. No, there are a lot of things that I would like to do with observations, applying, extracting, providing the community with catalogs of filaments, for instance, from a spectroscopic redshift survey of SDSS spectroscopic galaxy from the SDSS simulation or future survey like Euclid and all. And it can be done with the current state of the algorithm, I think, with the handling of the complexity of the size of the sample and all. I think it can be done, but it can be also improved with the handling of the distortion of in the redshift space that we have in actual galaxy redshift survey. It can be done by other methods, but as I said, the collapse of the elongation to make it spherical and all. So yeah, this is one of the perspectives of the work, is to identify filaments from LTSS or whatever a redshift survey to provide the community with the features that I have been showing you, like the width and all, that are usually applied a posteriori when using disperse algorithm. And then we are saying, okay, I'm taking a look at 2 megaparsec around the curve. Here you would have a more quantitative local description of the width and the association of galaxies. So yes, this is something I'm working on, and I hope part of my future job.
Okay, thank you. And finally, last question is, at the end of your talk, you mentioned a bit machine learning, but you seemed a bit skeptical about machine learning techniques. Why the community on the other side is very enthusiastic, and we see more and more papers, especially in cosmology, using machine learning techniques. There are different directions which have been taken. One is just a mapping from the distribution to cosmological parameters, and the other one is more kind of forward modeling. That's the one that you are mentioning, where using differentiable techniques, you can go back to the cosmological parameters and iterate. So, any comment on this point? So, I am enthusiastic, machine learning enthusiastic, even though I'm not very expressive in that sense. So I'm sorry if you get it to the opposite of it. But I am very enthusiastic, and what I mentioned here is mostly meant for the efficient use, in the sense that we can, if we can understand what is being learned and how it's being learned, then maybe just taking the example of the mapping between, I've seen some papers using deep learning that are trying to map the dark matter distribution and the galaxy distribution to emulate hydrodynamical simulations, or to go back to reconstruct the dark matter density field from the observation of galaxies. So this can be seen as a tool of deep learning that we can apply, and that's it, we get our answer. And what I mentioned here is more that if we have a better understanding of them through, I don't know what, for instance, physics is one avenue for that, we could learn something about the physics that is being learned instead of just viewing it as a tool. So I'm even more enthusiastic than just applying machine learning. I want to have access to its understanding to better do cosmology. I don't know if it makes sense, but in my head, it's a bit. And any of the tools that you have developed would be useful in a machine learning framework? The first one is making use, the principal graph algorithm is making use of the Gaussian mixture model, which is part of machine learning, unsupervised machine learning methods, even though it's simplistic, not neural networks and all. But the same kind of idea is followed by the statistical physics, for instance, to explain more complex algorithms like neural network, and identify phase diagrams of the algorithms. Properly speaking, the one I've been developing, I don't know, but Okay. Thank you very much. So the tradition is to ask to the room if there are any questions. No. Okay. So thank you. And now there will be deliberation.
Yes. So maybe okay. So should I connect to the Zoom and then you guys leave? Ça va? Okay. Because we need.
Who is leaving? You are leaving.
Just a second. Huh? So
Pour l'instant,
we
parce qu'en
have
fait,
to
c'est les
make
autres
sure
C'est là, donc c'est bon. Il était temps, hein.
Connection, connection.
Tout le monde est là, ce coup-ci? Très bien. Donc, je vais le faire en français, hein. Oui. Ouais. Donc, Tony, comme tu as pu t'en apercevoir, le jury a délibéré très, très longtemps. Beaucoup de choses à dire et de discussions. Ce qui en est ressorti, c'est qu'il y avait unanimité pour apprécier la qualité et la rigueur scientifique de vos travaux de thèse. Le jury a énormément apprécié la qualité pédagogique de la présentation, qui reflétait aussi la qualité manuscrite, parce que c'était très agréable à lire. J'ai pris beaucoup de plaisir moi-même à lire le manuscrit. Et donc, après délibération, à l'unanimité, le jury vous attribue le titre de docteur de l'université de Paris-Saclay. Et à titre officieux, parce que ça n'existe plus de manière officielle, les félicitations du jury. Félicitations.
Félicitations.
C'est pour ça, j'en mets le mien.
C'est le moment où je dois vous remercier, je crois.
Micro peut-être.
Les chercheurs, tu veux que je fasse ça? Staff scientifique, forcément.
Parfait, merci.
Marion, Laura, maintenant. Pour tout ce que j'ai appris ici. Je remercie les armes de l'équipe. Pas que l'équipe pour le contrôle.
Il est bien sur le Jabra là?
C'est une un peu pour un petit peu donc bien sûr des gens avec qui j'ai côtoyé au quotidien, Daniela, Céline, Marion, and Joseph, I will talk about it, but I really enjoyed what we were that we'll be working again together because a lot of stuff and I really enjoyed that. So thank you for that. Edouard, thank you a lot also. And my parents, merci pour avoir poussé dans les études et d'avoir l'amour de la science. Et ma copine qui m'a supporté, censeur anglais et français, durant ces 3 ans, on va dire, pendant la thèse. Et aujourd'hui, forcément, je remercie tous les membres du jury. Et enfin, j'espère que je vais pas adoré. On va commencer par Nabila. Je pense que je pourrais écrire un livre entier pour te remercier, mais on a besoin. Donc, je vais me restreindre. Merci beaucoup. Comme tu l'as dit, je vais avoir une chance. Et pas que, parce que d'avoir aussi cru en moi pour celle que tu avais en tête au début, et voilà. Voilà, je te remercie pour tout, mais pas que pour. Et Aurélien, je pense que sans toi, cette thèse, elle n'a pas vécu cette étape. Elle a été bien moins bonne, avec beaucoup plus d'astro, les observations. Et pas de tout ça, t'imagines? Alors que je continue un peu de ça. Merci beaucoup pour ta rigueur et tout ce que tu m'as appris. Et j'ai beaucoup apprécié le petit blog projet qu'on a fait ensemble, qu'on a commencé dans le cours de Navila pendant le confinement. C'est assez. Et de m'avoir fait découvrir tout ça. Et maintenant, je vais manger.
Tu peux mettre ton son parce qu'en fait il sort là.
Non mais là,
Ah bon,
de toute
là,
façon,
on-
on s'arrête.